Okay. First of all, can everybody hear me? Hopefully this is okay.
It's okay.
Yeah. Okay. Good. First of all, I would like to thank the organizers, Professor Ogawa and Professor Matano, and the local organizers at Berkeley for organizing this conference amid the pandemic. Today I want to talk about planar fronts of the Bidomain model. This is work that I have been doing with Professor Matano at Meiji University, Mitsunori Nara at Iwate University, and Koya Sakakibara at Okayama University of Science. Okay. So first of all, I would like to review a little bit of cardiac electrophysiology, which is what the equation here is about. So the heart is a pump that pumps blood, but the contraction of the muscle, the movement of the muscle has to be organized, and the organization or the orderly contraction of cardiac muscle is controlled by an electrical signal that comes from the cardiac pacemaker, which is located in the right atrium, which is here at what is called the SA node, and the electrical signal propagates through the cardiac muscle to produce muscle contraction. So here I'm showing some. I would like to show some movies here. So this is a rabbit heart, an experimental preparation that comes from the Tokachovo lab at the University of Minnesota. So what you're seeing here is a visualization of the cardiac, the heart electrical signal. And this is a spiral wave. So usually the electrical propagation in the heart is much more orderly. It does not form a spiral wave. If a spiral wave forms in your heart, you're in a lot of trouble. And this is an experimental preparation. So one can induce this kind of spiral wave by giving an artificial stimulus to the heart. Now you can also get patterns like this, which you can see the electrical signal. The electrical signal draws a figure 8 here, and so this spiral wave or the figure 8 clinically would correspond to what is called cardiac ventricular tachycardia. The heart is beating very fast. In the human case, this would correspond to about 200 about 200 beats a minute. Now, so that's very fast rhythm, but this kind of ventricular tachycardia can often devolve into what is called ventricular fibrillation, which is the pattern that you are seeing here, and this is fatal, as probably many of you know. And as you can see, these kinds of aberrations, abnormalities in the cardiac conduction can result in fatal arrhythmias. And one of the important goals of cardiac electrophysiology is to understand these kinds of arrhythmias. So I would like to talk about the histology of the heart. That is, what the heart looks like, essentially. If you look inside the heart is made up of bundles of muscle fibers. And in the cardiac bidomain model, which is what we are going to talk about today, cardiac tissue is viewed as composed of two interpenetrating compartments, the intercellular and extracellular spaces. And the intercellular spaces are connected with each other through what are called gap junctions. And there's the extracellular space, which is the gap that is filling in these cardiac strands. And the physiological variables of interest, the variables in the mathematical equations that we will be looking at later on are the intracellular and extracellular voltages, the voltages inside and outside the cell. Now, although the heart is composed of many cells of this nature, the heart consists of many on the order of billions of cells, and therefore it is in modeling of cardiac electrophysiology at the organ level, one usually writes down a continuum model, which is a partial differential equation model. And what I've written here at the top three lines here are what are called the cardiac Bidomain equations. And let me explain where they come from and the meaning of this. So the first line, du dt minus FUS is equal to divergence of AI UI. This is AI grad UI. This is the current continuity equation as applied to the intracellular space. So UI and UE are the intracellular and extracellular voltages respectively. And divergence of AI UI, AI is the conductivity tensor of the intracellular space. So this term divergence of AI grad UI shows is just the conservation relation for the ohmic current that is flowing through the intracellular space, and this is equal to del U del T minus FUS. This del U del T corresponds to the capacitive current that is passing through the membrane. FUS corresponds to the ionic channel current that is passing through the ion channels through the membrane. And we also have this equation here, the second equation here, which is essentially the current continuity equation as applied to the extracellular space. These first two equations can actually be thought of as the continuum limit of this equivalent circuit diagram that you see on the right-hand side. So you can see that, so the intracellular resistive network, and there's the extracellular resistive network that are connected. These two networks are connected through membrane electrical circuit elements, which are composed of capacitor and a ion channel element in parallel. So the ion channel element FUS is controlled by what are called gating variables, and these are these variables control the opening and closing of ionic channels. So this is what is called the cardiac Bidomain model. So and as you can see, this is it looks like a parabolic problem with an elliptic constraint with some pointwise ODEs that govern S. Now the nonlinear ODE terms FUS and GUS are such that du dt equals to F and ds dt is equal to G are of Hodgkin-Huxley or FitzHugh Nagumo type. We'll come back to that later. And as I said, AI and AE are, we're going to be doing our work exclusively in R2. So these are 2x2 positive symmetric definite matrices. Okay, so under the condition that AE and AI, so AE was a positive definite matrix, AI is another positive definite matrix. When AE and AI are constant multiples of each other, where beta is a constant, then the equations that we had, the two equations that we had at the top here can be reduced to an equation solely for U is equal to UI minus UE. U is equal to UI minus UE. One can write this equation just in terms of U, and we just have a reaction diffusion type equation. And this model here is called the monodomain reduction. This is just a reaction diffusion type equation. And this monodomain reduction is often used in cardiac electrophysiology simulations because it is easier to simulate than the bidomain model. But the bidomain model is known to be quantitatively a better model than the monodomain model, especially under extreme conditions such as defibrillation. That is to say, when you apply a large electrical shock to the heart so that you can stop a ventricular fibrillation episode. So the question that we want to ask is, well, we know that the bidomain model is quantitatively better than the monodomain model. Is it possible to identify some kind of behavior of the bidomain model that is qualitatively different from the monodomain model? So this is our question. And before I proceed to the main topic of discussion today, let me just summarize some previous results. So the model itself was introduced by Tung in the context of cardiac electrophysiology, which is what we are interested in today, and in a separate context in the lens and skeletal muscle by Matthias and Eisenberg, who are both physiologists. Since then, the bidomain model has been used as the standard tissue level model of electrocardiology and is very widely used in simulations. And many people have contributed to the literature, including Jim Keener, Sasha Panfilov, Carly Franzoni, and many, many others. So as for analytical results, there is early work by Carly Franzoni, Savare Ugar, Courier, Pierre Veneroni, but I would like to point out the very recent work of Kajiwara and Giga, where they prove some very strong local well-posedness results, in particular for these bidomain equations. So the bidomain model themselves can also be derived from a homogenization argument using an underlying microscopic model, and there has been some work in that direction as well. There also has been some interesting work on sharp interface limits, but as you can see, there have been some important analytical work, but what we want to do here is to try to understand some of the more qualitative behaviors of the solutions. So what we're going to focus on today is a simple model, which does not consider the S variable. It is this equation that we're going to consider. So del U del T minus FU is equal to divergence of AI grad UI equals to minus divergence of A grad UE. So this is just the first two lines of the equations that the bidomain model without the equation for S. And we are going to assume that AI and AE are spatially constant 2x2 symmetric positive matrices, definite matrices, and FU is a bistable nonlinearity. So the interest here in cardiac electrophysiology is in understanding pulse propagation, and therefore the underlying nonlinearities support a pulse. Here, with the bistable nonlinearity F, these equations support a front solution, and so we are interested in understanding the front solutions of these bidomain Allen Cahn equations, as we'll see. So the FU is a bistable nonlinearity that I think many of you in the audience are familiar with. So we have two stable fixed points 0 and 1, and alpha U being the unstable 0 of F. And as remarked before, if AE and AI are proportional to each other through a constant beta, then this equation here can be reduced to an equation just for U, which is UI minus UE, and we are back to the classical Allen Cahn equation that many of you know very well. So to make the comparison between the bidomain Allen Cahn equation and the classical Allen Cahn equation clearer, it is useful to rewrite the equation, the bidomain Allen Cahn equation, which is the first equation we have here, just as an equation for U. And we can do that, and what we see is that we can write this as del U del T is equal to minus LU plus FU. Well, LU is a Fourier multiplier operator in which the Fourier symbol is given by the quotient of QI times QE with respect to QI plus QE, where QI and QE are the quadratic forms that are defined by the conductivity matrix AI and AE. So this operator L we're going to call the Bidomain operator. And the Bidomain operator is a Fourier multiplier operator, and its symbol is a second order positive homogeneous rational function. So the only difference between so it's a fourth order homogeneous polynomial divided by a second order homogeneous polynomial when AE and AI are proportional to each other through a constant beta. You can do a very simple calculation to see that the operator LU just becomes the second order elliptic operator. QI is just so the symbol just reduces to the symbol QI, and QI is just a second order polynomial that is positive. So so as you can see from here, you can see that when AE and AI are proportional to each other, you just reduce the classical Allen Cahn equation. So let us review a little bit of what we know about the Allen Cahn equation. For the Allen Cahn equation, del u del t is equal to Laplacian plus fu. We know that there are planar fronts in every direction, and these planar fronts in every propagating direction theta, and where n is the direction of propagation, and the front solution UF satisfies this ODE, this ordinary differential equation, with limiting values of 1 and 0 at minus infinity and plus infinity. And all of these planar fronts are stable thanks to the maximum principle that is satisfied by the Allen Cahn equation. For the Allen Cahn equation, we have the maximum principle, and therefore you can sandwich any perturbation of the front by a front propagating in front of you and in the back, and by a sandwiching by the comparison principle, the perturbation is sandwiched by these two fronts, and therefore, because of the maximum principle, Allen Cahn fronts are stable. Now the question we want to ask is, what can we say about the bidomain Allen Cahn equation? First of all, we ask whether there are planar front solutions to the bidomain equation, and the answer is yes. It's actually very simple. It turns out that as soon as if you plug in this, if you substitute this planar front ansatz into the bidomain Allen Cahn equation, you immediately see that that ansatz, the planar front ansatz, will reduce to a one-dimensional equation, and that one-dimensional equation is just a rescaled version of the one-dimensional Allen Cahn equation. And therefore, the bidomain Allen Cahn equation also has planar fronts in every direction, and the speed is different depending on which direction you go, but the shape of the front is exactly the same, or a rescaled version of the planar fronts of the 1D Allen Cahn equation. Okay. So for example, if we consider the conductivity tensors of this nature, 1 plus A, 0, 0, 1 minus A, 1 minus A, 0, 0, 1 plus A, and both A and AE have to be positive definite, and therefore the magnitude of A has to be smaller than 1, then one can compute the speed of the front in every direction theta, and that speed is given by C star times K. C star is some constant times K, and one can also draw what is called the Frank diagram. And the Frank diagram is just this here, which is essentially a radial plot of the inverse of the speed in that direction. And depending on the value of A, this Frank diagram can be convex or non-convex. And as we'll see, the shape of the Frank diagram will have an important effect on what we'll discuss later. Okay, so the question is, are these fronts stable? So we have these planar fronts in every direction. In the classical Allen Cahn case, we know that all these fronts are stable. In the Bidomain Allen Cahn equation, what can we say? It turns out, surprisingly, that for some choices of AI and AE, and for certain directions, it turns out that these planar fronts are unstable. And this is the plot of the front propagating. As you can see, a small perturbation grows into and the wave develops into these zigzag waves. You can see a simulation here where a small initial perturbation quickly forms and quickly destabilizes the wave, and the wave front becomes is now zigzag. So here, so the front is actually moving from left to right. However, so the simulation is run in such a way that we are always looking at the front position. So the front itself is actually moving from left to right. Okay, so the question is, when are these planar fronts stable, and when are they unstable? And so now what we want to do is to do try to understand these stability properties. So what we're going to do is to move onto the standard thing to move to a coordinate system that moves with the planar front, and then to linearize around this planar front and to study the spectral properties of the linearized operator. So we introduce a coordinate system that moves with the front, and then we can rewrite the Bidomain Allen Cahn equation in this form. So in contrast to the Bidomain Allen Cahn equation that we had before, we acquire this C del U del C term because we are moving with the front now. And the coordinate is also rotated so that we want to study the planar front that is propagating in the direction theta. So now we linearize around this planar front, and so we are interested in looking at the spectral properties of the linearized operator that I have written at the very top here. And so if we understand the spectral properties of P, we will have some understanding. We will have an understanding of the stability properties of this front. So since the planar front is planar, it is natural to take the Fourier transform in the eta direction, which is the direction parallel to the planar front, and so the spectral problem for P decomposes into the spectral properties for that govern the perturbation of exponential IL eta, or the L wave number perturbations. So PL is the operator here that governs the growth of the wave number L perturbations to the planar front, and in order to study the spectral properties of P, what we just have to study is the spectral properties of PL. Okay, so this is what we have to study. We have to understand the spectral properties of PL, where to review, so this LL is this operator here, where you take the Fourier transforming C, you multiply by Q theta KL, and then come back. So here, as we've already decomposed in L, so these equations are just equations in C now. Now, the spectral problem for PL may look complicated, in fact, because first of all, this operator LL is a Fourier multiplier operator that looks rather complicated, and in addition to that, we have a nonlinear. We have a term f prime of UF, which is a function of C. It doesn't. It is not a constant. It depends on C. So we have a non-local operator that is not non-constant coefficient. So it looks rather complicated. However, there is an important observation that one can make. If we set L equals to 0, that is to say, if we only look at perturbations at 0, if we look at perturbations at 0 wave number, then P0 just reduces to the linearization of the 1D Allen Cahn equation around the front solution. So if we go back, so this is the planar front in red that is propagating in the xi direction. And then if the wave number is L is equal to 0, then we're only looking at perturbations that are parallel to the front. And therefore, the operator that governs those perturbations is going to be just the linearization of the 1D Allen Cahn equation around that front. And the properties of the operator P0 are very well known. So z equal to 0 is in the spectrum corresponding to the translation mode of the planar front, and the rest of the spectrum is in the negative real part of the complex plane. So what this means is that for small l, when L is small, the spectral problem of PL can be seen as a spectral perturbation problem from P0. So for small l at least, there is some hope that we can understand the spectral properties of PL just because we know the spectral properties of P0 very well. And there's actually a small algebraic trick that makes this work. So we let us look at this Fourier symbol Q theta IKL, this Q theta KL, and set L equals to 1. Now we have a polynomial in the numerator. We have a fourth order polynomial, and in the denominator we have a second order polynomial. We perform polynomial division so that pk is a second order polynomial and qk is just a linear function k divided by a quadratic function k. Now, so this kind of decomposition suggests that if you multiply, that things might simplify if you multiply the equation PLV equals to ZV, the eigenvalue equation essentially, by exponential of minus I alpha 1 LC because of this alpha 1 that is in this that emerges as you complete the square for PK. And if you do this, if you perform this algebraic trick, then one can show very easily that one can study the spectrum of PL just by studying the spectrum of P0 minus AL, where the operator AL is just a convolution against a pretty well-behaved kernel KL. And furthermore, this AL, when L is small, is on the order of L cubed. So it's actually a very small perturbation when L is small with respect to P0. And so with this, we can state our first instability result, stability/instability result. So recall that, so now, as we said before, we perform polynomial division of a fourth order polynomial divided by second order polynomial. And we had PK plus QK, and these are the coefficients here. Now, so the important quantity here is this red coefficient alpha 0. Now what we can show is that the operator PL has eigenvalue lambda is equal to the principal eigenvalue of the operator PL is given by lambda is equal to I alpha 1 CL, alpha 1 and C all being real, minus alpha 0 L squared plus order L cubed. So what this means is that if alpha 0 is negative, then lambda, the real part of lambda, when L is small, is going to have an alpha 0 L squared minus alpha 0 L squared component, and alpha 0 is negative, and therefore if alpha 0 is negative, you can actually be unstable. And this proof is basically just comes from this observation, this spectral perturbation argument that I just talked about in the previous slide. So what this tells us is that when L is small, that is for long wave perturbations, long wavelength perturbations, low wave number perturbations, then the sign of alpha 0 completely determines the stability of the front. And another interesting thing here is that this condition doesn't depend on the nonlinearity F. It only depends on the matrices AI and AE, the conductivity matrices AI and AE, because Q theta only depends on the conductivity matrices AI and AE. AI and AE defined the quadratic forms that define Q theta. So let's look at an example here. Let's say AI is equal to 1 plus A, 0, 0, 1 minus A. A is 1 minus A, 0, 0, 1 plus A. And one can compute this alpha 0 theta as alpha 0, this coefficient alpha 0 as a function of theta. This is a rather complicated expression of A and trigonometric functions, but it's easily seen that, that alpha 0 can actually be negative if A is greater than 1/2 and cosine of 2 theta is smaller than this number here. So let me and this algebraic condition that is derived from here, in fact, actually has a geometric interpretation in terms of the Frank diagram. So recall that the Frank diagram is defined as the inverse of the wave speed in each direction. And you just draw this diagram, Frank diagram, and it turns out that the directions in which alpha 0 is negative, that is to say, the directions in which the planar fronts are going to be unstable to long wavelength perturbation correspond to the directions in which the Frank diagram is non-convex. So these red regions here, when A is equal to 0.7, you have these red directions here in which the Frank diagram is non-convex, and those are the directions in which the planar front is unstable to long wavelength perturbations. And when A is small, A is equal to or smaller than 1/2, 1/2, it turns out that the Frank diagram is convex, and therefore planar fronts are stable to long wavelength perturbations. Okay, so what have we learned so far? What we've learned so far is that the sign of alpha 0, or equivalently the convexity of the Frank diagram, determines the stability of these planar fronts to long wavelength perturbations. And these long wavelength instabilities do not depend on the details of the nonlinearity F, because alpha 0 was just determined by Q, which was in turn determined by AI and AE, which were the conductivity tensors. It is possible, although I did not discuss this here, it is possible to derive a sufficient condition for stability, but the sufficient condition actually depends on F. And the sufficient condition that we can derive is not very sharp. When fronts are, for very, very short wavelength perturbations, it is not difficult. It's actually very easy to show that the fronts are stable, just basically because of the parabolic character of the equations. So the question now becomes, are there other kinds of instabilities? We have ruled out, so for example, if alpha 0 is positive, long wavelength perturbations and short wavelength perturbations are ruled out. Is it possible to have growth of intermediate wavelength perturbations that are neither, in which the wavelength is neither large or small? And for this, and it turns out that this highly depends on the choice of nonlinearity. And we here turn to what is often known as the McKean nonlinearity, which is a caricature of a bistable nonlinearity with linear plus a Heaviside function. And for this McKean nonlinearity, it is possible to compute many things, many quantities completely explicitly. And so for this, we can study the spectral properties of the planar front in detail. And here, what we can actually show is the following. So so first of all, we can derive an equation that is satisfied by the eigenvalues of the operator PL. PL was the operator governing the growth of the L wavelength perturbation. We can derive an equation that is satisfied by the eigenvalue as so. And using this explicit expression, we can show that under certain conditions, when alpha u, that is to say the intermediate zero here, this alpha u is very close to zero, then it is possible for lambda, it is possible to have for lambda to have a positive real part as long as beta zero, not alpha zero here, but beta zero is negative, as you can see here. If beta zero is negative, it is possible for lambda to be positive. So again, what we have shown here, without going into the details of the technicalities, is that for the McKean nonlinearity, it turns out that if alpha u is sufficiently small, an instability is possible when beta zero is negative. So the McKean nonlinearity is discontinuous, but we can actually show that if the nonlinearity f is sufficiently close to the bistable nonlinear to the McKean nonlinearity, like the pink line here, then the same conclusion holds. If beta zero is negative, then there is a smooth bistable nonlinearity, essentially one that is very close to the McKean nonlinearity, so that the planar front in that direction becomes unstable. So what have we shown so far? What does this tell us then? First of all, our previous results show that if alpha zero is negative, then this implies long wavelength instabilities regardless of my choice of the details of the bistable nonlinearity f. If even when alpha zero is greater than or equal to zero, in which case the planar front is stable to long wavelength perturbations. It is if we select the McKean nonlinearity or something close to the McKean nonlinearity, as long as beta zero is negative, you can obtain planar front instabilities. So in fact, one can go further. One can show that if AE and AI are not scalar multiples of each other, then there is always a bistable nonlinearity f that will make the planar front unstable in some direction. So this is a very this is in stark contrast. This is in very strong contrast to the classical Allen Cahn equation. In the classical Allen Cahn equation, planar fronts are stable for any bistable nonlinearity in any direction. However, I don't know what happened here. However, in the bidomain Allen Cahn equation, if AI and AE are not proportional to each other, which is precisely the case when the bidomain equation is not equivalent to the classical Allen Cahn equation, in that case, you can always find a bistable nonlinearity f so that the planar front is unstable in some direction. In fact, it is even possible to construct an example in which the planar fronts are unstable in every direction. So if we set a greater than square root of 2 over 3, and we set the nonlinearity f to be close to the McKean nonlinearity, then it turns out that we can construct examples in which every planar front in every direction is unstable. So this is essentially concludes the discussion here. So what we are working on now is to turn these linear stability results, spectral stability results, into nonlinear stability results, and for that you have to work a little bit harder. First of all, we work in a BUC, that is a space of bounded uniformly continuous functions. and we can show that existence uniqueness in this class, local existence uniqueness in this class, and then we can show that the L2 spectrum that we just actually discussed in the previous slides is essentially the BUC spectrum is essentially the same as the L2 spectrum, and to show this we have to study we have to do a careful estimate of the decay properties of the resolvent of the Bidomain operator. And with this, it is possible to show that that spectral stability in L2 that we discussed before implies nonlinear stability in BUC, and that if you are spectrally unstable in L2, then you are actually nonlinearly unstable in BUC. We have also obtained some results on the construct on some bifurcation results with respect to the width d. So one thing I had to say was that in order to do these nonlinear stability results, we have to talk about front stability on strips rather than whole planar fronts, because if we talk about planar fronts on the whole plane, the difficulty is that we do not have a spectral gap. Okay, so let me just end with a few more examples here. What we don't know, but we have some computational examples. That is, what we don't know, and but we only have heuristic arguments for, is what the final shape of the front is going to look like after a long time. And we suspect that the zigzag direction, these directions here, correspond to the directions that come about when you form the convex hull of the Frank diagram, and this seems to be supported by numerical evidence, and also let's see if I can go to the next slide here. And we can also consider spreading fronts where the front emanates from one point and spreads further out. And this is, we expect that these fronts would converge to wolf shapes asymptotically, which is the convex dual of the Frank diagram. Now, however, this is questionable whether this is really going to be true, especially, for example, if the planar fronts in certain directions are unstable. Even, as we said, even when the Frank diagram is convex, it is possible for certain nonlinearities, in certain cases, for the front to be unstable. So future directions include what happens with the FitzHugh Nagumo equation. So let me just run some simulations here. So the FitzHugh Nagumo equation, if you couple it with the Bidomain operator, as you might imagine, you sometimes you'll get the expected pattern of these zigzag pulses. However, in certain other situations, it seems to be that these waves will just break up break up and disappear. So we get some interesting new phenomena in the FitzHugh Nagumo bidomain model, and of course there's the important question of how does this all impact? This is all fun mathematics. What is this? What is the relevance of all of this to real cardiac conduction, cardiac electrophysiology? And we have some. So people have. So it's not clear, but Colli Franzoni, who has worked a lot in cardiac, who has been a leader in cardiac electrophysiology for a long time, has been suggesting for some time that non-convex Frank diagram could be very relevant for cardiac arrhythmias and cardiac ischemia. And Sasha Pamphilov recently has given us some very interesting suggestions on the instability mechanisms that we found and the fast sodium current. Okay, so this is my final slide. So my collaborators are Professor Hiroshi Matano at Meiji University, and with whom I did we are doing all of this, and with whom I've collaborated from the very beginning of this project. Professor Nara, Mitsunori Nara at Iwate University has been working working with us primarily on the nonlinear stability instability work, and Koya Sakakibara at Okayama University of Science has been working on the numerical methods and the scientific computing that is associated with our problem. Thank you very much for thank you very much. That's all.